All right. So, hello everybody. Good morning. Now your midterms are over, so we can come back to the wonderful process of learning more about relativistic physics. And so today we are going to talk about today is going to be lecture number 18. February 24th, 2021. So when we talk about relativistic physics, the origin of relativity or the special theory of relativity is rooted in Maxwell's theory of electromagnetism, right? Can anybody tell me why? In what way is relativity rooted in electromagnetism? Anand? Leon? Sai? Sai?
Is that because light is an electromagnetic wave?
Because what?
Light is electromagnetic wave and its special relativity is based on speed of light.
Right. So it's ultimately because of the wave equation, the electromagnetic wave equation, and that the electromagnetic wave equation happens to be to not be invariant under Galilean transformations. Right. So what we find from when we learn about electromagnetism, right, is that electromagnetic fields obey these equations. Right, and these are known as Maxwell's equations. So and these are the equations in differential form. So you can also write down the same equations in integral form, right? So the first equation is the first line. These two equations are Gauss's law. This is Gauss's law for electric charges. This is Gauss's law for magnetic charges. Then this is Ampere's law. Sorry, this is Faraday's law. And this is Ampere's law. And this one last term, This is called the Maxwell term or the Maxwell correction. So up till Maxwell's time, these equations were known in this form, right? Maxwell's contribution was to realize that, well, if changing magnetic fields induce electric fields, then and there is also a corresponding effect in terms of changing electric fields, which introduce changing magnetic fields, right? And just to label some of the quantities, rho of x is the charge density. And J x actually just J of x is the current density, the electric current density. Okay. And we are taking these to be time independent static sources, right? So there is no dependence on x here. So if you have time dependent sources, well, then that can lead to modifications of your you will need to include another set of equations here to supplement Maxwell's equations, which are basically Euler's equation. It's called the continuity equation, which says that divergence sorry, not divergence, yeah, divergence of J is equal to minus d rho by dt. This is called the continuity equation. It basically says that electric charge is conserved. So now, so what happens in this with these equations is that if we set rho and J both to 0, right? So you're talking about the source free case. What do these equations reduce to? Well, you get divergence of E is equal to divergence of B is equal to 0. You get divergence of E is equal to minus dB dt. And you get divergence of B is equal to mu naught epsilon naught dE. Right? So the time dependence of these equations is encoded within these last two equations. Right? There is no time derivatives in this expression. So now what we can do is, so one equation writes the electric fields in terms of the magnetic field. The other writes the magnetic field in terms of the electric field. So what we can do now is we can just take one equation, substitute in the other, right? So here we have curl of B. So what we can do is we can take the curl of Faraday's law. That means we take the curl of this expression. So on the So on the left, we get curl of E. On the right, we get curl of dou B, dt by dt. But then we can commute the curl and the time derivative, right? Partial derivatives commute in this way, right? So I can put the curl inside the time derivative. Then I can substitute this expression. So I get minus mu naught epsilon naught So on the right, I have curl of E. On the left, I have curl of E. On the right, I have mu naught epsilon naught d square E. Right? So now this becomes a differential equation purely in terms of the electric field, right? I apologize that I'm speaking at the same time, which I realize is not a very professional thing to do. And I'm making undue use of the fact that in the pandemic, all teaching is online, but I hope you can forgive me. Many of your videos are turned off, so I have no idea what you are doing. For all I know, you all could, be having some kind of a fancy guest party or something, right? So now, what about this expression here? So we can use, there are some vector identities, right? So when you have two vector fields, let's say A and B, and you take, so, or let's take three vector fields, A, B, C, and you take A cross B cross C, right? So this expression here is like this expression. It's similar with A equal to B, and give instead of the vector field A, we have the operator, this gradient operator, the del. So what is this expression? This expression is curl of A B cross B dot C, right? So it looks like this: A dot C times B minus A dot B times, right? So this is a vector identity. You can confirm it at your leisure. In fact, I should confirm this at my leisure now, because sometimes I get the signs wrong. Anyway, we will check that whether I have the correct sign or not. So if you set A is equal to B, right, then what you get is, on the right you get, so what we'll do is we'll put the B, so A dot C is the number, B is a vector, right? So I'll put the B before, I can put the B before the number, after the number, it doesn't matter, right? So I'll put it before the number, and I'll say A is equal to B, so this becomes A times A dot C, and then minus A dot A, this becomes A square C, right? So now, if we substitute the gradient operator instead of this vector field A, what does it become? I think this should be minus plus. Again, you can double check that. Okay. So if you do this, what happens? Now we replace this a with the gradient operator, right? So what happens to a dot c? So if you replace a dot a with gradient, this becomes divergence of c. And if you replace a square, this becomes del square. So this becomes gradient of the divergence of vector c plus, and I think I might have been right about the sign, minus a square becomes del square vector c. Okay, so not cross product, grade divergence. So let me write this on a different page, slightly bit more clearly. C paste so if you place A by the divergence, this means that you get curl of C is equal to the gradient of the divergence of C minus del square C. Okay. What is this del square C? This is a vector. This is a vector of quantity, right? This is a vector quantity. The left hand side is a vector quantity, so it has indices ijk. So the right hand side also has to be a vector quantity with indices ijk. Now, when we replace this, so now let me write this in terms of E, the curl of E. So this becomes the gradient of the divergence of E minus del square. Right. And what is the divergence of E? It is 0 because we are working in the source-free case, right? We're saying that there is no charge density. So this becomes minus del square. Now what is del square? Del square is this operator, right? Dou x square, dou y square, dou z square. So what is del square vector E? Del square vector E is, well, it's this quantity, right? This is a vector expression. So you have to apply it for each component of E separately, right? So you get d square Ex by dx square, d square Ex by dy square, and so on, right? So this is the left hand side of our equation. And the right hand side of our equation becomes this minus mu naught epsilon naught. So we are left with this minus del square E, this expression is equal to minus mu naught epsilon naught del square E dt square, right? So we get plus, right? And yeah, we can check that this is the wave equation, and since I get the wave equation, then tracing my steps back, I know that I got the correct sign here. Okay. Now, what are the solutions of this equation? Let's look at a simple case. Let us set EY is equal to EZ, or actually, let me set EX is equal to EY equal to 0, right? So this equation has three components, right? X, Y, and Z. So I am left with one component, the Z component, which is mu naught epsilon naught, like this, right? Now I'll make things even simpler for myself. I will say, so EZ, let me make EZ to be a function only of X and T. So it doesn't depend on Y or Z. So that means these derivatives are 0. So what does my equation reduce to? It becomes this. So let me draw a picture here like this. Let's say this is the x-axis, this is the y-axis, this is the z-axis. So a small thing, this is not a right-handed. So actually, if I want to make this a right-handed coordinate system, I have to put the y-axis over here, x, y, z. Otherwise, it will be a left-handed coordinate system. So here, what is happening is that if you look at the electromagnetic field, it only has a z component, right? So this expression is telling me how this electromagnetic field component is changing as I move along the x-axis. And this is telling me how it's changing in time. Okay? So something like this is happening, right? And we can, let's see what are let's write down some assumption here. Let's say Ez is equal to some E naught times cosine kx minus omega t. Okay. This is my ansatz. Ansatz is another fancy German word for, it means for assumption, right? We are assuming, let's try this as a test solution. So when I take the second derivative of this with respect to the position x, what will I get? I get cosine gives you minus sine gives you minus cosine, right? And you get two copies of k outside. So you get minus E naught k square cosine kx minus t. I can write that as minus k square Ez, right? E naught times cosine this is equal to Ez. Similarly, if I take the second time derivative, what happens? I get minus omega square Ez. I'll get two copies of minus omega, and again the same thing will happen, cosine minus sine minus cosine. Right? So next page. So what I get now is I have this equation. dt squared. I make this assumption and this answer gives me minus k squared Ez minus omega squared Ez. Putting these expressions back in here, what do I get? On the left hand side, I get minus k squared Ez, right? And Ez is a function of x and t. And on the right hand side, I get minus omega square mu naught epsilon naught Ez again as a function of x. Okay, so Ez is common, I can cancel it on both sides. And I'm left with this expression, which gives me the dispersion relation, right? Which tells me that k is equal to plus or minus root of omega, k is equal to plus or minus omega root of mu naught epsilon naught. Right? How should I interpret this? Well, this is a plane wave. This is the expression for a plane wave. What is the wavelength? The wavelength is related to k. K is equal to 2 pi by lambda. What is omega? Omega is equal to 2 pi f, where f is a frequency. Right? And the wavelength and the frequency are related in this way. Lambda times f is equal to the velocity, or I should say speed of the wave, right? So what is lambda times f? Lambda times f is equal to 2 pi by k. F is equal to omega by 2 pi. So this becomes omega by k is equal to v. Right? This is just very basic physics, right? I mean, this is like first year of your bachelor's, first year of college. I hope you all remember. So if you look at this expression, what do you get? You see that omega by k is equal to, we can forget about the plus or minus sign. That just tells you which direction the wave is propagating in. You can look at the absolute magnitude. This is equal to root of mu naught epsilon naught, which is equal to the speed of the wave, right? Now, what are the values of mu naught and epsilon naught? I think I forget the results from time to time. I should look up the values. So we have epsilon naught, which is called the permittivity of free space. right? It's equal to 8.854 times 10 to the minus 12. This F is the F by M. F is force, right? F is force. So this is force, right? What about mu naught? Mu naught is called the permeability of the vacuum, and it has a value equal to, in SI units, of 1.256 times 10 to the minus 6, and let me see, is equal to H by M. H is the unit of magnetic field, right? Henry. Is that right? H is Henry. No. Yeah. No, sorry. The unit of electrical inductance, not this one. So if you look at what is mu naught epsilon naught, what is 1 by root of epsilon naught mu naught? Well, let's do the calculation. I have a calculator here. I plug these in. I get 1 by root of 8.854 times 1.256 times 10 to the minus 12 times 10 to the minus 6. This becomes 10 to the minus 18. When I take the square root, I get 10 to the minus 9, and I can put that in the numerator to get 10 to the 9. In the denominator, I have 8.854 times 1.256. So I can take the product of these two, and then the answer I get is 2.998 times 10 to the 9. Right? And the units of this will turn out to be meters per second, right? They have to be meters per second. So this is the velocity, the speed of the waves. So what are Maxwell's equations telling me? Maxwell's equations are telling me that in free space, when there are no sources, electric fields, and I can repeat the same procedure with magnetic fields also. Instead of I can substitute this expression. I can take the curl of this equation and repeat the same steps. Again, I will get divergence of B. I'll set that equal to 0. So I'll get the same expression for P. Excuse me. I'll get exactly the same expression for the magnetic field. So the electric field and the magnetic field, they both have solutions which are given by plane waves, which are traveling with this velocity. Now this velocity happens to be suspiciously close, and this is an 8. To the speed of light, right? So when you have such amazing coincidences, you are tempted to look for an explanation. So what is the explanation? The explanation turns out to be the fact that light is propagating waves consisting of oscillating electric and magnetic fields, right? This is what Maxwell's equations tell us. So now, and the velocity of this wave is this, what we know to be the speed of light, 3 times 10 to the 8 meters per second, right? But now this is the interesting part. If we look at this, equation, the wave equation, okay, so I'll write it like this now, 1 by c squared dt squared. So c is the speed of the wave. This equation, right, what it has it has x and t, right? So what is this? This is with respect to some observer O prime, right? There is some observer O, sorry, not O prime, O, whose frame of reference has some coordinates x and t, right? And in those coordinates, that observer is making a measurement of this electric field, right? And they find that, well, the electric field, has this form. Has this dependence on x and t. Now, we have been studying relativistic physics, so obviously the next natural question is to ask, what if you have some observer O prime moving with respect to O, right? So you have this wave, right? This is the O reference frame. And then you have some observer O prime. O prime is moving with respect to O, again in the x direction to keep things simple, with some velocity, let's say u naught, right? Now, what is the speed of this wave? The speed of this wave is, as seen by O, the speed of this wave is c, right? So what should be the speed of the wave as seen by O prime? Now we already have the benefit of knowing special relativity, so we can say that the speed of the wave with respect to O prime, let me call it V prime, will be what? V minus u naught over 1 minus V u naught by c square. We have the benefit of hindsight. We know that the velocities have to add in this way. And what does this become? This becomes c minus u naught 1 minus c u naught by c square. This is equal to c. right? So this wave, it propagates at the same speed, no matter which observer is looking at it, right? The velocity of the speed of this wave doesn't change. Right? And this was the point at which Einstein discovered a collision between two different pillars of fundamental physics, right? So the first pillar was that of Newtonian mechanics, right? And then there was another pillar. These are my representation of pillars. This was the theory of electromagnetism. Now you have to remember that electromagnetism was not very old by the time Einstein came into the picture. So Einstein started to think about these things at the age of 16, right? So that was 1895. Here we have a 16-year-old Einstein who is thinking about what he would see if he was sitting on an electromagnetic wave and the wave was moving and he was moving along with the wave. He was pondering this question: what will I see? Right? And now, if you apply your Galilean intuition, which comes from Newtonian mechanics, right? Galilean intuition tells you, well, that if you are moving along with the wave, right? If you're moving, you have a wave and you're moving with the wave. What do you see? You see the wave as being frozen, right? There are no oscillations, right? But now this presents a paradox, because these equations tell you that the wave exists in the first place because there is some time dependence, there is some oscillation in the magnitude of this electric field. So if you are an observer moving along with the wave, you see an electric field which is frozen in space, which has a which has some undulations, but those undulations are not changing. But the paradox is that, well, if they are not changing, then you can't have the undulations in the first place. The wave will not exist, right? So this led him to think, well, that there is some problem somewhere, right? And the problem was with the Newtonian intuition. What was the Newtonian intuition? It was that if you were traveling with the wave, the velocity of the wave would be zero, right? So the Newtonian intuition was that if u naught is equal to c, then as seen by O prime, the velocity of the wave would not be moving, it would be frozen. And this was the error. So mathematically, right? So this leads to a conflict between these two pillars. Mathematically, the way to understand this is by looking at this equation right? And you perform the transformation to the moving frame of reference. So in the moving frame, you have x prime is equal to x minus u naught t, and you have t prime is equal to t, according to the Galilean transformation, right? So if you apply this to this expression, what do you get? You find that the resulting expression x prime squared 1 by c squared dt prime squared, but then you get another term which looks like this, something like d square ez dx dt. So according to the Galilean transformation, right, you get this extra term. But if you have this extra term, then you won't have your wave won't look the same. You won't have a wave equation, right? And if you could give some wave-like solution for this Ez as seen by the moving observer, then that wave-like solution would not necessarily have the same speed c, right? So if the Galilean intuition is correct, then this would give you a way to determine the absolute state of motion of any observer, right? Because by examining the electric field, you could find out if it showed the presence of this term or not, right? You could perform some sort of optical experiment whose results would depend on the existence of this term, right? And if you perform this experiment and you didn't find this term, then you would say that you are at absolute rest. But if you found this term, and I think there would be a factor of 1 by c also in here somewhere, or not 1 by c, 1 by u naught. If you found this term, then you would be able to measure your absolute speed with respect to other observers. Right? So this would violate the proposition that there is no absolute space or absolute time. It would violate the notion of relativity of motion. So this is what led Einstein to reject this transformation equation, right? And to look at the Lorentz transformation. And when you do the Lorentz transformation, what you find is that, well, this equation becomes invariant under the Lorentz transformation. It remains exactly the same. Right? So this was the origin of the special theory of relativity. You can also say it was the origin of quantum physics also. Well, that was a separate set of considerations, but related. They are not completely independent. So what we'll do in the next class is we will look at this equation. We will understand its behavior under Lorentz transformations, and we will also go on to look at how the electric fields themselves transform. So when you look at the electric field also should have some dependence on the observer's frame of reference. So we will look at how these fields should transform, right? And yeah, so I'll stop here for the day and see if you have any questions. Questions? Okay.